Hey guys, welcome to your Chapter 17 video, Part 1. Redux. This is a resubmission of the video that I made last night. I felt like a sloppy mess when I recorded this yesterday. So I wanted to go back through this, discuss the two probability models that are in Chapter 17, which for some of you guys you've seen misassigned problems, probably in both classes that's happened at this point, where some of these questions of how many ways can such and such happen out of like 20 or 25 or 30 trials and all occur? Well, let's get into that. It's not going to come up on your quiz if you're watching this. If you're a fourth blocker and you're watching this before your chapters 14 through 16 quiz, none of this stuff will come up on that quiz. But what we're going to begin with is a discussion of Bernoulli trials. Okay, both the geometric and binomial models that we're going to use work with these Bernoulli trials. Well, Bernoulli trials have the following three characteristics. That's two outcomes and only two. They're independent probabilities of success. So the probability of success on the first trial does not affect the probability of success on the second, etc., etc. And third, the probability of success is the same on each trial. So it's just a constant the whole way through. So what we're going to do, and we're going to do it in a lot less time than we did in the 40-minute video yesterday, is look at 4 examples and determine whether or not we have Bernoulli trials here. So rolling a 1 on a die, which counterintuitively is a Bernoulli trial, because it sounds like the wording suggests that you're just recording the 1 or the fact that the 1 happened or that it didn't happen. So you can lump together 2 through 6 is sort of your failure, 1 is your success. So the first condition is met. We'll keep the current color scheme. There are 2 outcomes. Do we have independence? Sure, because the roll of a die doesn't affect the next roll. So we have independent trials. And then in C, third condition is that you've got a constant probability of success. Well, P, if that stands for your probability of success, it's just going to be equal to 1/6 because there are 1 of 6 sides of the die that have a 1 on it. Q, therefore, would be the complement 5/6. Okay, so that is a Bernoulli trial. Okay, second example, flipping a coin. Sure, you've got 2 outcomes, heads or tails. You have independent probabilities of success, independent trials here. Okay, 1 head or tail doesn't affect the next being a head or tail. Remember that the law of large numbers doesn't say that if you go tail, tail, tail on 3 consecutive flips of a coin, that the coin owes you heads to counterbalance. Okay, it's just that if you take many trials, eventually you're going to get to a number, a relative frequency of success that approaches the true probability of success for that event. Okay. Last case here, constant probability of success. Sure. P, if that stands for the probability of success, is 1/2, and Q would be 1/2 as well. Okay. Now, I don't think a coin is quite that balanced. A penny, I don't believe it's like 49%, 51%, something like that, but close enough. Close enough. All right. Third example here. So because those conditions are met, we have a Bernoulli trial. Drawing an ace from a deck of 52 cards. Well, this could be a Bernoulli trial. It looks from the wording here like it isn't because they don't mention that you're replacing the card that you're drawing. So even though, yes, there are 2 outcomes, you either get an ace or you don't get the ace, the independence condition is not met. Okay? Because if you draw a card, let's say it's the ace of spades, well, all of a sudden, where the first probability of success was 4 aces out of 52 cards in the deck, so 1/13th, now having taken that ace out of the deck, you are down to 3 aces out of 51 cards, so the probability of success for your next ace is 1/17th. So you don't have independence, and therefore, you also don't have a constant probability of success. P is not constant. Okay? So, in conclusion, this is not Bernoulli, okay? And then lastly, the value of a die roll, well, that is not Bernoulli for the following reason. We have 6 outcomes. Why don't I be consistent with how I word this? Let's write 2 outcomes and then the X to indicate that condition's not met. And then the second condition is independence. Sure, we have independence here. That's not an issue. Each die roll shouldn't affect the result of the next. And P is constant. Well, no, it's not, in some sense. If for these exactly 2 outcomes, P is equal to the probability of success, and Q is equal to the probability of failure, then P and Q don't even make sense here because you have more than 2 outcomes. P and Q don't apply. All right, so there again, you have trials that are not Bernoulli. Okay. All right, from here, let's look into our first model. And this is the simpler of the two. The geometric model is as such. X is the number of Bernoulli trials until success. Okay? So if you can think about these Bernoulli trials as just being, in a relatively simple example, coin flips, because that meets the condition. 2 trials, independent trials, and a constant probability of success of 50%, where your success could be flipping a head, or you could define success to be flipping a tail. Just depends upon the problem. So where does this come from? Well, your table here comes from a tree diagram, really, where for each Bernoulli trial you have success or you have failure. Okay, the probability of success on the first coin flip is P, or 50%, okay? Or you could have a failure, which is Q, denoted Q. Visually, it's the opposite of the P. It's symmetric with the P, which is kind of nice, which is also 50%. So here would be the case where if X is the number of trials until success, you could have in your first trial, the probability of success would just be P. That's where this comes from right here for your first trial, okay? So for your second trial, if you failed on the first attempt, you've got another chance. You either succeed or you fail. And if you succeed for your first time on the second random trial, it took a failure, denoted with Q, whatever probability that is, times P to get there. So this is the probability that you succeed for the first time on your second random occurrence, okay? And you can just repeat this ad infinitum. That is to say over and over and over again indefinitely. So 2 failures would be QQ. So third flip of the coin or third Bernoulli trial, you again have success or failure. There are only 2 outcomes. Well, your first success being on your third trial would have a probability of Q times Q, so Q squared, times P, the probability of success, which again is the probability that you succeed on that third trial. Okay, so notice there's a pattern here with the exponents. And that's really right here. It's embedded in the geometric model equation that if you're wanting to find the probability of success on the xth trial, the xth could be 5, okay? You're going to have 4, oh, that's not a very good circle. You're going to have 4 failures preceding it, followed lastly by success. So to get the probability of success on the xth trial, you just take Q to the x minus 1. There are x minus 1 failures that precede that last success, okay? Well, the expected value and the standard deviation for the geometric model, they are as follows. Oh, I don't want to get a pen out. I don't want to write in pen on the smartboard. The expected value of the geometric model is it's derived for you on the 3rd page of chapter 17 in a math box. It uses an infinite geometric series to do that, but it's kind of an interesting look at how that works. I'm just going to present them to you, partly for the sake of time. This is, the mean is 1 over p. Standard deviation is the square root of q over p squared. Okay? Those two things are not on your stats reference sheet. However, the binomial model, which we're going to look at here in just a few minutes, that does have the mean and standard deviation on the reference sheet. So these two things you really need to know by heart come time for the test that we'll take over chapters 13 through 17. Okay? Is there anything else I want to say about the geometric model for now? Yeah, there is. Yes, there is. Okay. So when we're talking about the geometric model, you can look at it a number of different ways. In some sense, your geometric model is represented in the tree diagram at the bottom of the screen with these red circles, the P, the PQ, QP, the Q squared P. You would have, repeating this process again, Q to the third, P, Q to the fourth, etc., etc. Okay, those red circles in some sense denote the geometric model. However, your model can be represented with this equation because look at what the table is doing. It's saying, okay, if x is equal to any given number, well, you can plug any number you want in for x into your equation. The table says we'll find the probability of your first success on your x case. Well, that's what the equation does. So this equation right here is a more concise version of the table-based probability model we've used in the past, and it's a more concise version of the probability model represented in your tree diagram. Okay? So it's okay for someone to give you a probability model that is an equation. It just needs to do two things. It needs to be able to take a certain trial, or at least when it's Bernoulli, it needs to take the values of the random variable, and it needs to find the probability of success on that value. Okay? All right, so let's practice with this. Only about 6% of people have O-negative blood, which is a, what was it called? Universal. I believe it's a universal blood type. O-negative blood types can donate to A, B, and AB blood types, but they themselves can only take O-negative blood. So they're really helpful when it comes to blood drives for others, but they have restrictive, there are restrictions on the bloods that they can take. All right, if donors line up at random for a blood drive, how many do you expect to examine before you find someone who has O-negative blood? What's the probability? It's the first question. What's the probability that the first O-negative donor is found among the first 4 people in line? Okay, well, let's say that X is equal to the number of donors checked till first O-negative blood type found. Okay? And I'll just stop with O-negative. So the probability of success here, notice the geometric model uses these Q's and P's. For each problem where you're using the geometric model, please write out what your probability of success is, write out what your probability of failure is. At the bare minimum, if you're doing that correctly, that's an opportunity for me to give you partial credit on a test or a quiz. So the probability of success for any individual person is 6%. Probability of failure, therefore, is the complement because there are only 2 outcomes of 94%. Oh, and I should back up and say, yeah, we do have Bernoulli trials. For each individual person, there are only 2 outcomes: O-negative blood type or something else. And the probability should be independent. Now, we're going to kind of wave our hands there a little bit because realistically, for a blood drive, you would expect that people are coming to the blood drive in families or in groups that are related through blood. So maybe it's not fair to say that if dad is A, that's not going to affect whether or not you are an AB, or O-negative blood type. But we'll assume that's the case, okay? Because honestly, we can't answer the question unless we make that assumption. And then the third piece is that, do we have a constant probability of success? Sure, 6%. Is there a constant probability of success for any individual donor. All right, so we've defined our variable. We have our P's and our Q's all lined up. And we want to know, how many do you expect to examine before you find someone who has O negative blood? Well, that's just the expected value of X, which last slide we said the mean of the geometric model was 1 over P. So that is 1 over 0.06, which is 16.7, which is approximately 17 people that you expect to need on hand before you find your first universal blood type. Okay? All right, so there's the first chunk answered. Second chunk here, they want to know probability that the first O negative donor is found among the first 4 people in line. Okay, so now they're asking a very different type of question. They want to know that the probability that X is less than or equal to 4. Okay? That is to say that your first success is your fourth, third, second, or first person checked. Well, that just breaks down like this. In fact, you can skip what I wrote first here, the underlined piece, and just write the following. That's the probability that your first person would have O negative blood, plus the probability that your second person would have O negative blood, plus the probability that your third, and finally the probability that your fourth would have O negative blood types. Okay? So, breaking these probabilities down, well, the geometric model says you just take Q to the x minus 1 times P. Let me erase this chunk here so you can better see it. Q to the x minus 1 times P. So if we want to know the probability that the first person is our success, that's Q to the 1 minus 1 times P, plus Q to the 2 minus 1 times P, plus Q to the 3 minus 1 times P, plus Q to the 4 minus 1 times P. Well, Q is 94%, boxed right here. So this is, in the first case, you just got Q to the 0th times P is 0.06, plus Q squared is 0.94 to the first here times 0.06, plus 0.94 to the second times 0.06, plus 0.94 to the third times 0.06, and that simplifies to, what did I find? 0.2193. We'll box that bad boy up, and there you go. There's a little bit of work with the geometric model. Okay, on to the binomial. The binomial is a much more interesting model. The geometric is kind of weak in that it just tells us when the first success could occur. The binomial says if you take n number of trials, you could say that n is the number of coin flips, going back to that analogy. If n is equal to 20, if I flip a coin 20 times, and my probability of success, if we want to say that success is flipping a head is equal to 50%, Q therefore would be 50% as well, the complement. How many coin, or what's the probability that of my 20 flips, I see 8 heads, or 12 heads, or 10 heads, or something like that? So it's more robust. It does a little bit more. Well, the binomial model is broken into 2 chunks. The probability, if X is the number of successes in n trials, the probability that your random variable equal some number of successes, that capital X equal lowercase x, is equal to, this is called n choose x. That's a combinatorics piece right there. And we're going to kind of explain that next slide, but what I wrote in parentheses, you'll have to work with manually, but it's not something you have to understand in great detail, even though I'm going to try to scratch at the surface of it. Okay, so there are 2 chunks here. This chunk, which I'm underlining, that we're going to explain next slide. This guy, we'll explain this slide a little bit. Let's go ahead and fill in the expected value and the standard deviation of this model. Well, these are on your reference sheet, and they are, just want to make sure I write these down correctly. NP for the mean of the geometric or binomial model, And the standard deviation of the binomial model is NPQ, all under a radical. Okay. So I said that we would explain a little bit of that circled chunk now, and we do that in this slide. Well, let's set up a scenario here. Let's say that I've got my number of trials is equal to 6. Okay, and let's say we're talking about no, I want to use 5. Let's say we've got 5 trials. Let's say we're talking about coin flips. So P is the probability of a head being flipped, and that's a 50% probability. Q, therefore, is the complement probability of a tail. That's also 50%. And X, let's say that I want to see the number of ways, or I shouldn't say the number of ways, the probability that of my 5 flips, I have 2 heads, okay? Well, notice, if you think about your random occurrences as slots that you're filling, okay? Blanks that can either become heads or tails, okay? Well, any way that you do this, and notice that there are lots of different ways to do this. You could have head, then head, followed by 3 tails. You could have head, tail, tail, head, tail, etc., etc. You can rearrange in lots of different ways which 2 of the 5 random occurrences, random flips of the coin, give you the 2 heads that you want. But regardless of where the 2 heads fall in these 5 situations, the probability of one sequence with 2 heads, 3 tails will always be found as follows. That's a P, that's a success, times a failure, times a failure, times a success, times a failure. And they don't necessarily have to be in this order. If your first flip was a tail and your second flip was a head, you could have Q times P, but still you've got 2 successes and you've got 3 failures out of that bunch, okay? So the circled portion right here only finds the probability of success one time. It doesn't take into account that you can rearrange in these 5 flips of a coin. You can rearrange and have those successes, have those heads occur in different places. It could be first and second flips, it could be second and fourth flips as it is here, it could be third and fifth, etc., etc. So that's the portion that this N choose X fixes. Because if all you do to find the probability that you get 2 heads out of 5 flips of the coin is you say, oh, okay, that's success times failure, failure, failure. You're not taking into account all the different ways that can occur. All right, so before we get into this circled combinatorics piece, I need to present to you the factorial. And I think that in some of your math classes, you would have already seen this. I don't know where this falls in the curriculum, the high school curriculum, outside of AP Stats. I want to say I interacted with it in maybe trig, maybe. I remember seeing it in high school, but I don't remember what class we used it in. Regardless, n factorial is defined to be n times n minus 1 times n minus 2 on down the line down to 2 times 1. So if I take 5 factorial, that would be 5 times 4 times 3 times 2 times 1, which is, okay, now what does how does 5 factorial apply? Well, 5 factorial answers the question. Let's say that I've got 5 objects, okay? These are my 5 objects. I could have a black circle, I could have a red circle, I could have a green circle, I could have a blue circle, And then lastly, let's go with some of the color choice here. I could have an orange circle, okay? There we go. Okay, so those are my 5 objects. 5 factorial is the number of ways I could fit those 5 objects into 5 different positions at random, where the order matters. Notice, I've got 5 choices to fill my first slot. All right? But then, once I use one of those 5 objects, let's say that the red object had been chosen to fill the first slot. Okay? Well, that leaves me with 4 remaining ways that I can fill the second slot. Okay? And then let's say that, for instance, green had filled the second slot. Well, that leaves me with 3 remaining ways that I can fill that third slot, etc., etc. Okay? So what 5 factorial does in this particular case is it tells us the number of ways you can arrange 5 items or 5 things in 5 positions, okay, where the order is important here. So notice that red followed by green would be a different way than green followed by red, because that would be one of the different 5 objects filling that first slot, one of the different 4 objects filling the second. Okay? So a factorial tells us the number of ways we can arrange in objects. So in factorial would tell us, this chunk right here would tell us if you have n things, the number of ways you can arrange those in order in n positions. Okay? All right, so the factorial. The factorial solves the problem of how many different ways you can get 2 tails, or 2 heads out of the 5 flips of the coin. What you've got on the next slide is busy, busy, busy. Okay? What's going on here is that you have 120 rows of 5 slots. Okay? So you've got upper left here, 1, 2, 3, 4, and 5. That is one way in which you could order 5 objects. Then that's followed by 1, 2, 3, 5, 4. Then it's followed by 1, 2, 4, 3, 5. So go through the whole page if you want. I don't recommend it. And you're going to see that all 120 combinations of ways that you could rearrange 5 objects is listed. So that is your 5 times 4 times 3 times 2 times 1, okay? Which is also represented here as just 5 factorial, okay? Well, that's clearly way too many ways to find that we have just 2 heads and 5 flips of the coin. So you've got this denominator, which means something, okay? Let's see if we can understand a little bit of what this denominator means. Let's start with the blue underlined piece, the 3 factorial. Well, 3 factorial, written to the right here, we know is 3 times 2 times 1. Well, if I just want to know, and this is why some of these numbers are highlighted in red, if I just want to know which 2 positions or which 2 of my 5 flips of the coin are heads, I don't really care about the numbers in black. I just want the first 2 numbers. I want to know, okay, well, my heads could occur as first and second, my heads could occur as first and third, etc., etc. So whereas 5 factorial gives us all the 120 different orderings of numbers 1 through 5, I'm going to divide out 6. Let's see how to explain that. I'm going to divide out 6 cases for every combination of 1 and 2, 1 and 3, 1 and 4, etc. because I've got 3 times 2, 2 times 1 numbers left over that are used in that 5 factorial ordering. So everything in black I don't care about, and I divide that out. So notice every blue honeycomb piece here is really, that is just one chunk of the answer that I want. I just want the 1 followed by 2. I just want the 1 followed by 3, the 1 followed by 4. I don't care about the black stuff. So that is divided out. The 3 factorial is the number of ways that your extra numbers can be arranged. Okay, so that's the first part of the denominator. On the second piece, the 2 factorial, that is obviously breaks down as 2 times 1. Notice, if I want to know which of the 5 positions my 2 heads can occur in, 1 followed by 2 is 1 ordering within our 5 factorial, but that's really just the same answer that I care about as 2 followed by 1, because those red numbers are telling me that my heads can occur on the first and second, or in that honeycomb to the right, the second and first trials. Well, that means the same thing. I just want to know which 2 of the 5 my heads can occur in. So the other chunk of the denominator here divides out all the duplicates, the duplicate red pieces. 1 and 2 is the same to me for this problem type as 2 then 1. 1 then 4 is the same to me for this problem type as 4 then 1, etc., etc. So every blue honeycomb has a pair that you could link it to with the green arrow here that is saying the same 2 of the 5 flips would be heads. Okay? So before we look at a problem together, let me show you how the factorial works out. Obviously, I'm just scratching the surface of factorial stuff here. There's a lot more that can be said. If you take a discrete and combinatorics math class in college, or if you take probability, whether or not it's calculus or non-calculus based, you'll work more with the combinatorics chunk right here. Okay? But let me show you how to work with it. Let's say we've got n is equal to 7, and I want the number of ways I can choose x to be 3 objects. Okay? So what this combinatorics piece would do, in parentheses, if it's n choose x, it says, well, your numerator is just n factorial. Your denominator would be x is equal to 3. I don't want to do that yet. X factorial on bottom times n minus x factorial. So filling in these numbers, that would be 7 factorial over, if x is equal to 3, 3 factorial times 4 minus 3, or excuse me, 7 minus 3 is 4 factorial. So we have 7 times 6 times 5 times 4 times 3 times 2 times 1 over 3 times 2 times 1 times 4 times 3 times 2 times 1. Aha! So there's some nice cancellation that can occur. The 4's, 3's, 2's, and 1's drop out. 3 times 2 times 1 is all just 6, which cancels with the 6 up top. So the combinatorics thing here tells me there are 35 ways, if I have 7 objects, I can choose 3 of them. Okay? All right, so again, we're scratching the surface. The thing that you need to get from this slide is how to use this, and you'll see more of it down next slide. Okay? If this quick explanation of the combinatorics formula doesn't make sense, I wouldn't stress over that too much. All right, come on, next slide. There we go. Let me check the time here real quick. And we're not doing great on time, but we're doing the best we can. Okay, so suppose 20 donors come to the blood drive. What are the mean and standard deviation of the number of universal donors among them? What is the probability that there are 2 or 3 universal donors? Well, this is going back to example 1. Here, the variable is different. We'll define x to be the number of successes in 20 trials, where the 20 trials are just the donors who are having their blood checked. Okay, the probability of success is the same as before, 0.06. Probability of failure is 0.94. And being a little redundant, is equal to 20. So the expected value of this does follow a binomial model for the following reasons. Okay, the binomial model looks for the number of successes in n trials. Well, we've got 20 trials. We want the number of successes is really asked about later in the question, but you have Bernoulli trials because just as before, you have 2 outcomes. Either someone has O negative blood or they don't. The trials are independent. One person's blood type shouldn't affect the next person's blood type. And finally, the probability of success, 0.06, is constant. So this is equal to n times p, which again is on your stats reference sheet, which is 20 times 0.06, which is 1.20, which is approximately, you expect to see one person and 20 donors with this blood type, which makes sense because earlier with the geometric model, we said it, you would expect to go through 17 people before you find one person, your first success, to have O negative blood type. So the two models are sort of confirming each other to some extent. Okay, so the standard deviation of our random variable is square root of NPQ, which is the square root of 20 times 0.06 times 0.94, which comes out to be, this I've not worked out yet, 0.06 times 0.94, square root of 1.128, 1.06. Okay, I didn't mean to switch up the color here. Let me just do that. Okay, so we've got the mean, we've got the standard deviation. They want the probability that there are 3 or 2 universal donors. So first chunk was answered of the question. So they want the probability that x is equal to 2 or 3. Well, that's just the probability that x is equal to 2 plus the probability that x is equal to 3. Well, let's take this guy and solve him over here. Probability that x is equal to 2. There are 2 pieces of the binomial formula. The combinatorics piece, so that's n choose x times p to the x, q to the n minus x. Notice the number of successes and the number of failures total will be equal to n, the total number of trials. Okay, so this breaks down as follows. This is where n is 20, x is 2, the probability of success is 0.06, we're looking for 2 successes, probability of failure 0.94, that would be 18 failures. So this chunk is 20 factorial, which we could write as 20 times 19 times 18, and I'll put that as 18 factorial. You go 18 times 17 times 16, etc. But there's a reason I'm going to leave it as 18 factorial. Denominator is 2 factorial times the difference between 20 and 2 factorial, which is 18 factorial. So there you have the cancellation from the numerator to the denominator. 2 factorial is just 2 times 1, which is 2, canceled with the 20 to give us 10 times 19 up top. Okay, that's messy. Let me clarify that just a little bit. 10 times 19 up top. Okay, times 0.06 squared, times 0.94 to the 18th. Simplify that on your calculator real quick. 10 times 19 times 0.06 squared times 0.94 to the 18th, and you get 0.2246. That's a probability you'd see 2 people with this universal blood type. Okay, let's break down 3 next. So that would be 20 choose 3 people. Probability of success is 0.06 to the 3rd. Probability of failure 0.94 to the 17th. Let's break down the combinatorics piece here. That would be 20 times 19 times 18 times 17 factorial over 3 factorial times 20 minus 3 factorial, 17 factorial. So those again canceled. 3 factorial is 3 times 2 times 1, which is 6. The 18 and the 6 cancel here to leave us with 20 times 19 times 3. There's a 1 left on bottom, times your 0.06 to the 3rd, times 0.94 to the 17th. Well, this simplifies to give us 20 times 19 times 3 times 0.06 to the 3rd, times 0.94 to the 17th, which is 0.086. 0.0860. Okay, so the probability that you see 2 or 3 people with that universal blood type out of 20 in all is equal to 0.2246 plus 0.0860, which is a final answer of 0.086 plus 0.2246, 31.06%.